Hi, this is the demo video for TextWorldExpress, simulating text games at 1 million frames per second. I'm Peter Jansen, an assistant professor at the University of Arizona, and this is joint work with Mark Alexandre Code at Microsoft Research in Montreal. So this work is about text games and using text games as virtual environments to teach agents a variety of natural language tasks that involve common sense reasoning, like instruction following or navigation or picking and then placing objects and so forth, which are common tasks that are explored in so-called embodied research environments. And if you weren't around in the 1980s, then you might not have much experience with text games, but we can think of virtual environments as existing on sort of a continuum of simulation fidelity. And on one end, you have sort of photorealistic environments like AI2 Thor, which are visually high fidelity representations of a variety of home environments. And then next we have sort of voxel-based environments like Minecraft that simplify the spatial reasoning required by agents by having a world that's sort of built out of these large Lego-like blocks, but the agent sort of still moves around in 3 dimensions. Another example simulator is the NetHack learning environment, which is a 2-dimensional dungeon crawling game that is rendered using ASCII characters. Then sort of last on this list, we have Zork, one of the most popular text adventure games. And rather than being rendered in 2D or 3D, we see that Zork is rendered not spatially, but linguistically as natural language text that's given to the user. And the user has to interact with the game by giving it natural language commands back, like open door or read letter or so on and so forth. And just sort of briefly here, even though it's sort of counterintuitive, but as rendering fidelity decreases, the action spaces here tend to increase. So for example, the AI2 Thor and Minecraft environments, they tend to have fairly small action spaces, mostly things like move and then a single interact command, whereas games like NetHack or Zork tend to have very large action spaces with many dozens of commands like eating or taking or reading or moving and so on and so forth. So even though they don't have a rich spatial rendering, they tend to have a very rich action space. Just to help ground this work, here's an example of a few steps of Zork. The game starts off by saying you're in an open field west of a house. There's a small mailbox here. And so as a virtual agent or a human, you need to read this environment description, understand what it says, formulate some plan of action to take, and then start entering in natural language commands one at a time that sort of implement that plan. So you might think, okay, we see a house, we see a mailbox. Do we go in the house? Do we check the mailbox first? Let's check the mailbox. So we type in the command open mailbox, and then it says back, opening the mailbox reveals a leaflet. And so, okay, let's read it. Welcome to Zork, and so on and so forth. Okay, let's go in the house, go north. You're behind a small white house. In one corner of the house, there's a small window, which is slightly ajar. It sounds like we might be able to climb in that window. Open window with effort. You can get into it, and so on and so forth. These text-style virtual environments are becoming a new research methodology for exploring a lot of complex multi-step reasoning processes in natural language agents. There's a couple of reasons for this. One, they're hard. For example, the current best agent completes only about 12% of the game of Zork. So there's still a very long way to go. But more generally, they seem to require a mixture of sort of common sense knowledge and domain-specific reasoning abilities to solve. For example, you need to navigate around rooms, you need to know the locations of common items, you need to know the affordances of common items, like that sinks can be turned on to get water, or that fridges are containers that make things cold, and so on. As a research paradigm, text games are very rapidly gaining popularity. In a recent review, I found that over 100 papers have been authored just in the past year or two, or a few years, I should say. And one of the reasons is that text worlds have a much lower barrier to entry than 3D games. A single person can author a new text game You don't need a team of 3D modelers and game designers working for years to construct it, and so on and so forth. Because text games as a research paradigm for natural language processing has only been happening for a few years, one of the current challenges is tooling. The tools that are used are quite old, legacy tools, and in many cases built on the original tooling from the 1980s that were used to play those original text games like Zork. And so the simulation speed can be quite low. To give you an example of this, right now simulator speed goes from a high of about 300 samples per second all the way down to about 1 sample per second, which really limits sort of the speed that you can run your experiments, especially when modern reinforcement learning models typically require hundreds of thousands of steps really to start making progress on many of these tasks. So in this work, we introduced TextWorldExpress, which is this new and high-speed simulator designed from the ground up for natural language processing research that's about 3 orders of magnitude faster than existing tooling, reaching anywhere from 250,000 steps per second to over 1 million steps per second, depending on the particular mode that you tend to use it in. And so this in this tool, we re-implement 3 common benchmark text games that tend to be used in a lot of NLP research papers. We have Cooking World, which is sort of an instruction following game where agents need to follow a recipe to cook a meal. There's TextWorld Common Sense, which is sort of this pick and place game where agents need to pick up things off the floor like dirty socks and place them in their sort of canonical, correct common sense locations, like putting dirty socks in the washing machine. And then finally, Coin Collector, which is sort of this navigation games where agents have to wander around an environment looking for coins while avoiding distractor objects. To get a sense of just how fast TextWorldExpress is compared to existing simulators, we can sort of have a quick look at this table here. So to orient to the table, up here at the top are common 2D and 3D simulators like AI2 Thor or MineRL, which is a wrapper for Minecraft, or the NetHack learning environment. And then down here are our text game simulators. And so there's 3 existing text game simulators that are quite popular for NLP research out there. The first one is TextWorld, which is a toolkit for making small research-oriented environments with sort of parametric variations. There's Jericho, which is an API that's used to make your life easier when you want to play existing interactive fiction games like Zork using natural language agents. And then there's a new simulator that we just released a few months ago that's largely centered around simulating science domain experiments, particularly elementary science domain. And so the speed of these 3 simulators varies quite a bit, anywhere from 1 sample per second for Jericho, all the way up to a maximum of around 300 steps per second for TextWorld. And again, this is largely due to using legacy tooling. TextWorldExpress speeds this up quite a bit. At its slowest, it runs at about 30,000 frames a second, while at its fastest, it can run near 4, sometimes even 5 million frames a second. So this is really anywhere between 2 and 4 orders of magnitude faster than existing tooling. It's quite a big leap. These days, most natural language processing research is done either in Python or in JVM languages like Java or Scala. And so we provide APIs for both of these languages with the Java libraries outperforming the Python libraries by about a factor of 10. The library can also be used in 2 modes. We have an online mode that generates games on the fly, and a pre-crawled mode where you sort of pre-cache the games that gives you an additional win of about an order of magnitude in terms of performance. I should also note that these are single thread performance figures here, and TextWorldExpress is designed for easy threading. And so the fastest we benchmarked the API on just common desktop hardware is about 35 million steps per second on a 16-core 32-thread CPU, which means you can do about 1 billion steps in about 30 seconds. In contrast, that would take a single thread of TextWorld about 2 months here. So it's really dramatically changing the scale that experiments can be run on here. So very briefly, one question that naturally presents itself is, why do existing text game simulators run so slowly? There are two answers. One of them is that, again, existing simulators rely on legacy tooling, much of it built in the 1980s, like something called the Z machine interpreter that was built to run Zork on computers in the 1980s. So the tooling and the specifications are pretty old. But the second reason is a bit counterintuitive, and it relates to something called valid action detection that we'll illustrate here. So imagine that you're playing a cooking game, and it starts off as the following here. Welcome to the kitchen. In the corner you see a fridge whose door is closed. On the counter is a cookbook and a red pepper. To the west you see a pantry. This is sort of a toy example of one of these kitchen cooking games. The way that a human plays a game is that they think of the next action they'd like to take and they type it in. So for a cooking game, we know that we probably want to read the recipe so we know what we need to cook. And so we might type in read recipe or read cookbook as an action that they'd like to take. And then on the simulator side, it accepts that action, it parses it, and then it creates and delivers a response. Something like, the recipe says it's time to make fried peppers. First, chop the peppers, then fry them on a stove, and so on and so forth. And so this is how most of the existing tooling works, because it's designed for humans to play games. With text game research, the simulators tend to look a little bit different. So at a given time step, we still start off with our observation, but because text games tend to be extremely hard for contemporary agents, nearly all agents typically require the simulator to provide a list of possible valid actions that they could take as the next steps in the environment. This is sometimes called the valid action handicap. So for example, we could read the cookbook or take the red pepper or open the fridge and so on and so forth. It's worth noting that generating this list of valid possible actions tends to be very computationally expensive. Part of the reason why it's expensive is that existing tooling for text games was never designed to do this. And so in the worst case, like for the Jericho API, you actually need to generate a large list of all possible things an agent could ever type, which is basically the cross product of the actions list and all the objects that the agent could ever see, and then try each one out individually by cloning the simulator, running it, and seeing the ones that generate valid actions. So that's why it can be extremely slow and give you frame rates of about a frame per second. In contrast, TextWorldExpress was really designed from the ground up to be a research environment for natural language processing and make this valid action generation very quick, which is why we get many orders of magnitude savings in this tool. And so, of course, once the simulator makes that list of possible valid actions, the agent can pick one that they'd like to perform, and then that expensive process of generating the next valid actions at the next step repeats itself again. And so you just keep on taking this hit. So taking a step back a little bit, TextWorldExpress supports standard features in text game simulators, like generating gold paths that an agent might take to help automatically create training data. But it also has a kind of cool new feature that's possible mainly because of its speed, like path pre-crawling, where you can actually pre-crawl through all the possible states in a game, either to pre-cache the game for speed, or to help teach an agent more than one solution to the game to help encourage robustness by finding different possible paths that generate solutions. And so to help ground this a bit, let's imagine that a game can be represented as a graph, where the nodes of the graph represent specific states the game world is in. And so for the cooking game we just looked at, for that toy cooking game, we might imagine that the initial state is something like the observation: you're in the kitchen, you see the fridge, counter, cookbook, and so forth. And so TextWorldExpress generates a list of all possible valid actions that you could take at a given time step. And so we can start to crawl all possible sets of actions that an agent might take and progressively build this larger and larger graph. Here it's shown as a tree that represents, or where the nodes represent the states and the edges represent the possible valid actions that the agent might take, like reading the cookbook or taking the pepper or opening the fridge or moving west and so on and so forth. Here there's only 4. In many text games, there's many hundreds that could be taken at a given time step. So here we've only gone 1 step deep into the game. But you can imagine repeating this again and again, trying out all possible action sequences at each state, to down all the way to some sort of maximum number of steps, and seeing what happens and storing the results so that you can pre-cache them for speed or do additional analyses or whatnot on it. Existing simulators really struggle with this because of their speed. Even if you're very patient with the original TextWorld, you can crawl a maximum of about 4 to 5 steps. But with TextWorldExpress, it really lets you crawl massive paths of about 10 to 12 steps, typically in minutes, which is, in many cases, more than enough steps required to solve many of these games. And so it opens up these advantages in terms of speed from pre-caching or finding multiple solution methods to teach agents robustness or whatnot. So TextWorldExpress is available on GitHub, and our repository includes the libraries, the APIs, example code, and quick start documentation. It's also pip installable on Python, the hope being that we've lowered the barrier to entry enough that folks can really get up and running in just a few minutes. If you'd like to explore the 3 benchmark environments, which are Cooking World, TextWorld Common Sense, and Coin Collector, the GitHub repository also includes a web server demo that allows you to pick an environment and explore it by selecting possible valid actions generated by the simulator at each time step, as we show right here. And so here we'll select reading the cookbook as our next possible action, and we see the list of ingredients and steps that we have to prepare this recipe in Cooking World. If you prefer to explore the text games using the console, we have a console demo in the repository as well that allows you to explore, again, all 3 games by interacting with them just by text in the console. And then, of course, we have a variety of example pieces of code in the repository that include benchmarks, the human console, and random agents, so that there's enough code to demonstrate the use of the library and get folks up and running and generating their own agents quickly. TextWorldExpress is available on GitHub at Cognitive AI Lab/TextWorldExpress, and it can also be installed in just a few moments using pip in Python. For any questions, comments, or feature requests, please feel free to open a GitHub issue. Thanks.